Hey, Wheaton North, Mr. Yergo here. We've talked a lot about bonds, and we've talked a lot about molecules, and we've shown in our Lewis dot structures how two atoms will share electrons. I want to talk more. I want to kind of dig into that a little bit more and talk about how exactly they're sharing electrons. What's actually happening between the two electrons of any atoms that are in a bond. Okay. So the option number one is that when you have two atoms and they have their outside electrons, one of those atoms could steal the other atom's electron, right? And this is what we think of as ionic. We've talked in the past about how ionic is a transfer of electrons, right? One atom is completely stealing the other electron away from the other atom. And that's because the electronegativity is much, much greater, right? There's a big difference in electronegativity. If this atom is really electronegative, meaning it pulls electrons towards itself really strongly, then it's like a really unmatched tug of war. It just rips the other electron away. Okay. Now that's ionic. That's always going to be between a metal and a non-metal, right? You should know that ionic is always metal and non-metal. We're going to deal more in covalent. Okay. There's a kind of image of us moving that electron from one to the other. Here's a good image that shows an ionic bond. And this simulation, I like this because it's really showing that transfer of electron. Watch that one little yellow dot around the sodium. It ends up completely around the chlorine eventually. And notice the large difference in electronegativity. Chlorine is 3.0 versus sodium's 0.9. Okay. Most of the cases that we're going to deal with involve what's called covalent bonds, where they're sharing. Now, there's two ways that they can share electrons. They can share equally or unequally. We'll talk about equally first. Okay. If both atoms are equally strong, or they have equal electronegativities, then they're going to pull on those electrons just as much as the other one, right? So if you're imagine you're in a tug of war with someone and you're equally matched, the rope doesn't really move one way or the other too much. Same thing with these electrons in between. If the electronegativity is very similar between the two. Okay, here's a good image of nonpolar covalent. They're both 2.5 in electronegativity, so the difference is 0 between the two. And if you notice, when they come together, the electrons are kind of flying around. They're not favoring one atom or the other. They're kind of equally dispersed throughout the entire thing. The third option is that they share unequally. So if one atom's electronegativity is slightly greater than the other, then they'll share unequally. Think again of a tug of war. If one atom is pulling a little more strongly, that rope is going to go towards one end more than the other. Okay, and here's a simulation that kind of shows that. That hydrogen's electron there starts out on the hydrogen, ends up mostly around the oxygen, but on average it's kind of hanging out with oxygen a little bit more because oxygen is a little bit more electronegative. But it's not so electronegative that it completely pulls it away. Hydrogen can still hang on to it a little bit. Here's a good image that kind of shows this too. Nonpolar covalent, think of these circles as like your electron cloud that's kind of surrounding your two atoms. If it's equal, then it's going to be equally dispersed around both atoms, right? A polar covalent is going to be dispersed around one atom more than the other. So the electron cloud is kind of getting pulled over on this side, okay? And then ionic, it's completely, they're not really sharing electrons at all. This one is just giving up its electron to the other. All right, we need to be able to predict what type of bonds we have, okay? And notice that this is predicting the bond type of single bonds. We're going to talk about molecules in a second, but and I want you to be able to distinguish between the two. A little bit different method between determining the bond type of single bonds versus molecules. Okay, so let's do single bonds first. You're going to use the electronegativity, which you can look up on the back of your periodic table. If the difference, the triangle, the delta means difference. If the difference is 0.4 or less, then we're going to say it's nonpolar covalent. Okay. If it's between 0.5 and roughly 2, 1.9 or 2, then we're going to call that polar covalent. They're sharing, but not equally. One is slightly stronger than the other one. And then ionic is metal and non-metal always, right? And they're usually going to be differences that are greater than 2.0. Okay. We're going to illustrate the polarity with a dipole moment arrow, what's called a dipole moment arrow. And there's an example. It's like a little plus sign that has an arrow on it. And let me kind of show you an example. So carbon, if you look on the back of your periodic table, there's a list of these electronegativities. And if you look up carbon, it has an electronegativity of 2.5. And sulfur should be 2.6. Some graphs say it's 2.5, but I think ours says that it's 2.6. So that's a difference between the two of 0.1, right? They're so close in strength, in electronegativity, that one is not going to pull the electrons away from the other one, okay? So that's nonpolar covalent. Look at carbon versus nitrogen. Nitrogen is stronger than carbon. It's 3.0 versus carbon's 2.5, so the difference is 0.5. So that's going to be polar covalent. And then if we look at an example like magnesium and oxygen, this is actually a metal with a nonmetal, and so it's going to be ionic. You can kind of tell right away, and the difference is 2.1. All these numbers are coming from the back of the periodic table. There's a small list of electronegativities. All right, now we're going to talk about predicting the polarity of the molecule overall. Okay, so think about it. You have an atom, or you have two atoms. Think of like water, right? Two atoms, you can figure out the polarity of that bond between those two atoms, but if it's part of a bigger molecule, we also want to know the polarity of the overall molecule, not just the little bonds that are making up the molecule. Okay. Again, we're going to use electronegativity. So determine the shape, and then we're going to use the shape to figure out the net polarity. All right, so let's look at water as an example. The bonds are oxygen and hydrogen. You can look up the numbers, and it's a difference of 1.4. Okay, 3.5 versus 2.1. So oxygen is pulling electrons up from this hydrogen, and it's pulling them over from this hydrogen, right? So the bonds are going towards the oxygen. The dipole moment arrow shows the direction that the electrons are getting pulled, so it's always to the higher electronegativity one. Overall, though, because we're going up and over, you would draw an overall diagonal arrow. Overall, the electrons are getting pulled towards the oxygen, and so we can just show that they're going towards the oxygen. Okay, this is what we would call an asymmetrical molecule. It's a bent shape, right? We would know from the Lewis dot structure and the structural formula that water is bent, and so there's nothing over here to kind of balance it out. It's not there's no way you can like say that this is symmetrical, really. And so the molecule is polar because there's nothing pulling in the opposite direction that would cancel that out. Okay, let's look at an example where it is nonpolar. All right, this is carbon tetrachloride. Our bonds, chlorine is much more electronegative than carbon, right? 3.1 versus 2.5. So electrons are getting pulled away from the carbon towards the more electronegative element, towards the more electronegative atoms. So, but notice how they're pulled in every direction equally, right? Because we have chlorines all the way around. It's like perfectly symmetrical. Because it's a symmetrical molecule overall, even though the bonds themselves are polar, this is a key point that you need to get. The bonds themselves are polar because they're a difference of 0.6. But the molecule overall is nonpolar. And the reason is because it's getting pulled 0.6 this way, but it's also getting pulled 0.6 the opposite way, right? And same with up and down. So the overall pull is actually canceled out because the molecule is symmetrical. So you have to know the shape in order to know the whether or not it's going to be polar or not. And that's kind of what I just said. Dipole moments cancel out, so it's a nonpolar molecule. Okay, I love this slide because it really kind of shows the truth behind this concept. Imagine X and Y are two atoms, and these are the electrons in between them, right? They're hanging out right between the two, so I would say they're shared equally, right? As we increase the polarity of the bond, we're going to do this several times, the electrons slowly get pulled more and more towards Y. So Y is getting stronger and stronger, okay? So at this point, the electrons are hanging out with Y slightly more than they're hanging out with X, and so that gives X a slightly positive pole, or slightly positive end, and Y a slightly negative end. So let's keep increasing the electronegativity of Y. It keeps pulling those electrons over towards itself, right? Eventually you'd get such a huge electronegativity difference that Y essentially has and owns those electrons, right? It's stolen them. And it becomes completely negative and X becomes completely positive. At that point, we would say we have ionic. But up here, they're shared equally, and so it's nonpolar. Anywhere in here, it would be polar covalent. And what this shows is that there can be a difference between two different polar covalent. Just because something's polar doesn't mean it's the same as everything else that's polar. It's like a spectrum, right? And so we're kind of just creating these cutoff points. We're saying 0.4 is our cutoff point between nonpolar and polar. but some people would say 0.2 or 0.1. It's kind of a spectrum. It's not really like a 3 different distinct categories. If you have any questions, be sure to write those down right now while you're thinking of them, and we'll see you in class. This is Mr. Yergler, signing off.